This video is about weakly modular functions, and we're going to come to this topic by way of what we've set up from the geometry of SL2Z already. My intention with this particular video is to give perhaps an alternative inspiration, if you will, for the definition of weakly modular form. So if you've looked at any text on modular forms, occasionally they'll give you some background about periodic functions and lattices, but oftentimes they'll just tell you that a weakly modular form is some function from the complex upper half plane into the complex numbers, which is meromorphic, such that it obeys the property that for some matrix gamma of SL2Z, f at gamma z is equal to cz plus d for some integer k times f of z. And this holds, of course, for all matrices gamma in SL2Z and all points of the complex upper half plane. But where does this definition come from? You can just accept the definition to start with and begin doing things, finding out facts about, proving theorems about modular forms, and eventually see, oh yes, this is an interesting definition, worthwhile, but perhaps it lacks some inspiration at the outset. Now, of course, the classical approach to this does provide some of that said inspiration. I want to take a slightly different approach to this, and perhaps some of you will find my approach to be more contrived and to be even more confusing than just accepting this, and that's fine, but for myself personally, I think this has more conceptual weight to it. It's just another perspective I enjoy. Maybe you'll agree with me. So the first point is that we want to, we have these geometric spaces, right? We've got SL2Z acting on the upper half plane, and this is the same thing as the collection of complex lattices with a specific orientation, modulo non-zero scalar multiplication. And one thing that we often do in geometry as a means to study particular spaces is we study the functions on those spaces. Essentially, often it's the case that the study of geometric objects comes down to the study of functions on them. For example, really a lot of the things that you learn about the real numbers, you learn through pre-calculus and calculus by studying different functions on the real numbers and looking at the interplay between the functions and numbers themselves. This also comes up, say, if we're studying manifolds, we really look at things like the smooth functions on that manifold, and perhaps if you've done some differential geometry or algebraic geometry, we also talk about sheaf theory, and basically stuff all gets done in terms of sheaves. Now, of course, if you haven't seen manifolds or algebraic geometry, don't worry, this is not essential stuff. But just to give you some idea of what's actually happening, in the realm of algebraic geometry, one can, instead of, thinking about some scheme, so that's the geometric object that algebraic geometers like to consider, one possible viewpoint is instead not even to think about the geometric space itself, but to think about the different possible sets of functions going in or out of that scheme instead. And in some sense, really all the information of the geometry is contained in that object's relationship to other objects. So that's a lot of words basically to just say that in order to understand these spaces, it would help to understand functions on these spaces. So first off, if we consider, well, what does a function defined on this quotient of the upper half plane, modulo SL2Z to the complex numbers, we can actually rewrite this instead of writing this as a function as such. Instead, we can consider functions that are defined on the entire upper half complex plane and simply demand that they are subject to the condition that f applied to gamma z is equal to gamma z. Of course, where this holds for all gamma in the modular group, all points of the complex upper half plane. Now, this definition is fine, but one thing about the quotient of the upper half plane by SL2Z is it's not a compact space. So remember, in topology, we say that a set is compact if and only if every open cover has a finite subcover. But really what this means in a qualitative way is that somehow the space isn't too big. It doesn't run off to infinity. It's sort of a finite kind of space. For example, spheres are compact, so are tori, but say the entire complex plane is not compact because you can, run infinitely far away from the origin. So we like compactness. There's lots of things we can say and do with compact objects. So we would prefer to actually make the complex upper half plane compact. So what we would like to do is consider instead the complex upper half plane union some point at infinity, where we think of all the elements, say if we look at the complex upper half plane, we think about everything that has very large norm being very far away from the origin as being very close to the point at infinity. Right? This is basically the same thing we do when we pass from the complex upper half plane to the Riemann sphere. We just add this point at infinity. So it makes sense to do a similar thing in this case and get a nice compact object. Now, of course, given any matrix of SL2Z acting on the point at infinity, well, it'll either send it back to the point at infinity, or depending on how we choose the entries of gamma, we can actually get any rational number here. So if we still want to consider this action of SL2Z, we'll also need to include all of the rational numbers. Sometimes as a shorthand, we can write Q hat to mean exactly this, the rational numbers union some point at infinity. Of course, when we take the quotient of the upper half plane union these points, really the point at infinity will be identified with all of the rational points as well. So this entire thing really just adds 1 point to our geometric object. But now this definition comes with a drawback. That is, if we recall the theorem of Louisville from complex analysis, this says that any bounded holomorphic function on the entire complex plane is constant. And this theorem actually generalizes to anything that is a compact Riemann surface. So if you're not familiar with the definition of a Riemann surface, again, don't worry too much about it. I will go on to discuss this in more detail in later videos. Basically, these are just manifolds where we use complex numbers instead of real numbers, and we have a little bit of extra structure. So the appropriate generalization of Louisville's theorem is that if you have a holomorphic function defined on any compact Riemann surface, then the function must be constant as well. So you can kind of imagine, these are very similar in flavor, right? So here we're just looking at open subsets of the complex plane, and really a compact Riemann surface is just some topological object that can be covered by open sets of the complex plane. So it's hopefully it shouldn't be too much of a stretch to imagine that this theorem generalizes to compact Riemann surfaces. Again, seeing as compact is sort of a simulation of the notion of finite, even though there aren't literally finitely many points. So what do we do then in this case? Because we want to study functions that somehow tell us geometric information about our space SL2Z acting on the upper half plane with its point at infinity. And all we're getting is that all we have there constant functions. Well, that doesn't carry a lot of information. That can't possibly tell us much about the geometry of this space. So two possibilities is that one, we could drop the condition of holomorphicity of our functions. And for instance, we could simply consider functions which are meromorphic. So this just means it's complex differentiable except for some collection of isolated points. Or instead of considering functions that have this transformation rule up above, perhaps it could be skewed slightly. So perhaps some constant, depending on gamma, gets multiplied out in front instead of it just being invariant to gamma. And in fact, what we're going to do is really consider both of these options at the same time. We're going to allow for both of these possibilities. So towards the end of figuring out what sort of constants we might want to allow to come in front for these transformations, having matrices act on points of the complex upper half plane, it's perhaps not too clear, well, what could we take as a constant coming out in front? Perhaps a determinant of sorts, and we'll see that does pop up in the theory. But let's consider the other realization of this geometric object. So stepping back from the point at infinity for a moment, if we just go back to SL2Z and the complex upper half plane, this is identified with the space of lattices modulo complex scalar multiplication. And so much in the same ways we did for functions on SL2Z mod the upper half plane, we can really, instead of considering these to be functions from the lattices modulo scalar multiplication, we can really just think of these as functions on lattices into the complex numbers, subject to the condition that f at lambda times capital lambda is equal to capital lambda. Now, of course, we realize that this, in the same way, this is too restrictive of a definition, so we want some constant coming out in front that depends on lambda. Now, this is perhaps a bit easier to come up with some ideas about what we might want to do here, because now this is a constant that depends on some number. So perhaps this could be, say, a polynomial in lambda, or something sensible like that. Well, let's consider for a second if we have some polynomial, and let's consider, so at this point we've taken some geometric space and we've added a point at infinity, and we said that this was a lot like going from the complex numbers over to the Riemann sphere. So let's think about what this looks like. So the Riemann sphere, this is the complex projective line. Let's think about what a polynomial has to look like to be defined on the Riemann sphere. So recall that the points of the Riemann sphere are pairs of complex numbers z0 and z1, where this is defined up to non-zero scalar multiplication. So we think of 2 points that are non-zero scalar multiples of each other as representing the same point. I have p, this polynomial, in two variables. Then if I evaluate it at this point z0, z1, well, this should represent the same point as p evaluated at lambda times z0 and lambda times z1. And what does it mean for 2 points to be the same in projective space? It means they're a non-zero scalar multiple of each other. So there should be some other scalar, say sigma, that I can multiply this by to make these equal. So, well, how will I obtain this? This won't be true in general. If you write down some polynomials, you'll find this isn't the case. But if every term has the same degree, that is, if the polynomial is homogeneous, then notice what will happen in this case is that this scalar that comes out front here, we have p evaluated at lambda z0, lambda z1. Since every term is the same degree, we can factor out lambda to the power of whatever that degree is. Call it k. So lambda k will come out in front, and that will be equal to lambda k times p evaluated at z0, z1. And so we find that this does obey the relation, and this will give us a well-defined function on the Riemann sphere. So since we're considering this geometric space where we've added a point at infinity, which is quite similar to taking the complex plane and adding a point at infinity, why don't we make this the demand and see what happens? So we're going to ask that our functions defined on the space of lattices to the complex numbers, instead of being invariant under scalar multiplication, we're going to let the scalar multiplication come out to some power, and this power k will depend on capital F. So now let's ask ourselves, what does this look like? We've figured out what this looks like on our space of lattices, and we want to get back to the original quotient of the upper half plane. And so having this identification of the space of lattices on one side, with the action of the modular group on the upper half plane on the other, we would like to find a way to translate between the functions on these spaces. And there ought to be a way to do it, because ultimately these are the same spaces, so each function should have a representation on the other end. Well, let's first suppose that we're given some capital F, which is defined on lattices, and we want to define a function little f on the other side here. Well, what we can do is that we know that the function capital F is defined on also the lattices lambda sub z. So in that case, we can define a function little f at any point z in the upper half plane, and we'll simply define it to be the value of this function capital F taken at the lattice lambda sub z. Alternatively, so that's going one direction. Alternatively, if we're given some little f, which is a function on the complex upper half plane, then we know that for some lattice lambda, that this is isogynous to lambda sub z for some particular z, right? We just take whatever the omega 2 vector is, and we multiply by its inverse to obtain lambda sub z. And then in that case, we'll simply define capital F at the lattice lambda to be f at lambda sub z, again, where this lambda sub z is the corresponding lambda sub z to the original lattice lambda. Okay, so this gives us a way to translate back and forth between functions on each side. And now we want to look at our transformation law, and we want to ask, well, what does this look like if we rewrite this sort of homogeneous equation for the capital F? What does this look like if we rewrite it in terms of f and what matrix multiplication does? So we start off with a function f evaluated at gamma acting on z for some gamma and z. And now by this dictionary we've set up, I know I can rewrite this as f evaluated at lambda sub gamma z. So if I consider the entries of gamma to be a, b, c, d, I can then rewrite this as the integer span of gamma applied to z is just az plus b over cz plus d. And of course, the other spanning vector is just 1 in this case. And then what I'd like to do in order to shift things around, I'm going to multiply by 1, essentially. But I'm going to write that as cz plus d over cz plus d. And that's going to be multiplying scalar multiplication by 1 of this lattice. And so the cz plus d in the numerator, that's the term I'm going to multiply into the lattice, and I'm going to keep the other term out in front. So this will become capital F evaluated at, and I'll have cz plus d to the minus 1 out in front. And the lattice becomes the span of az plus b and cz plus d. Now I'm going to apply my transformation rule. So I have this cz plus d to the minus 1 out in front, and our transformation rule says that I can pull out some scalar constant by putting it to some fixed power which will depend on capital F. So some k that depends on capital F. So this will come out in front, and I'll get the cz plus d Well, this is to the minus 1, and then I'm putting it to the k, so this will be to the minus k. And what I'm left with inside is the lattice that is the span of AZ plus B and CZ plus D still. And now the thing to recognize, though, is that if I were to take this matrix gamma, which is ABCD, and I were to apply it to the vector Z1, then this would give me the vector AZ plus B, CZ plus D. In other words, by the work we did in the previous video, we know that the lattice, which is spanned by Z and 1, is the same lattice on the nose as AZ plus B, CZ plus D. So, in other words, this term simply just works out to being CZ plus D to the minus k of f at lambda z. And finally, f at lambda sub z, well, that is just our function little f evaluated at z. And so here we obtain the transformation rule. F evaluated at gamma acting on z. This is just f at z with this term depending on the matrix coming out in front. CZ plus D to the minus k. Where now, since the k depended on the capital F, we can imagine the k instead depending on this little f. Now, something's slightly different here from the definition I originally wrote down, and that is I have a minus k here in the exponent. Well, notice, if I scroll back up here again, there's no reason, we'd never said anything about what this k has to be, right? Originally, we were thinking about it as the degree of some polynomial, but a priori, making this definition, this could be, say, for instance, any complex number. So we'll see that this is not the case, and we restrict to other values. But for our purposes, it wouldn't make any difference if we had started with negative k in that definition instead. And so had we started with negative k on the lattice side, then this would give us the transformation property that you've probably seen before for weakly modular functions. So that does it for this video. I think soon I'll be starting a new series splitting off, just talking about the theory of modular functions, modular forms. But I think I will continue this series, which will still be very relevant to that topic as well, but I'll focus perhaps a bit more on the geometry of things like SL2Z acting on the upper half plane, and how some of its subgroups act on the upper half plane, and that is very important for the general theory of modular forms as well.